Welcome back to part 3 of section 2.6, our final section in chapter 2. We're going to be talking about slant asymptotes. We've already talked about horizontal asymptotes and vertical asymptotes. Now we have a slant or oblique asymptote. It's a diagonal. Now a slant asymptote occurs only when the degree of the denominator is when the degree of the numerator is exactly one more than the denominator. When the degree of the numerator is exactly one more than the degree of the denominator. So if we look at the asymptotes for this, the vertical asymptote, set x plus 1 equal to 0, x equals negative 1. The horizontal asymptote, because the degree of the numerator is 2 and the denominator is 1, 2 is greater than 1, so there is none for the horizontal asymptote. And if you look, there is a slant asymptote because 2 is exactly 1 more than 1. So there is a slant asymptote. So the slant asymptote exists. We have to find it. Now, to find the slant asymptote, you divide the numerator by the denominator. So on the outside, we can use long division. I'll show you what that looks like. X plus 1. And on the inside, x squared minus x. And we need a placeholder for the plus 0. Now, to get x to become an x squared, you have to multiply by an x, excuse me. So that gives us x squared plus x. Remember, we're subtracting, so you distribute the negative, change every single sign. They cancel. You get negative 2x plus 0. And now to get an x to become a negative 2x, you multiply by negative 2. So you get negative 2x minus 2, and you subtract. So when you do that, you change all the signs. So you get 2. We get a remainder. Normally, that's not good. Normally, we don't want a remainder. But for this, it doesn't matter. I don't care what the remainder is. This is all I care about, the x minus 2. So my slant asymptote is at y equals whatever that quotient is, x minus 2. There's my slant asymptote. So I can sketch these. X equals negative 1. It's right here. Whenever you have a slant asymptote, you will not have a horizontal asymptote. Keep that in mind. So our slope is 1 and our y-intercept is at negative 2. So I'm just going to sketch the points for this line. And then I'm going to dash line through those points. So there's x equals negative 1, y equals x minus 2. So now we can find the intercepts. The x-intercept, real 0 the numerator, so x squared minus x equals 0. X times x minus 1 equals 0, so x equals 0. X equals 1. For our y-intercept, y equals 0 squared minus 0 over 0 plus 1. 0 divided by 1 is 0. So my vertical asymptote, x equals negative 1. Horizontal asymptote, there is none. Slant asymptote, SA for short, y equals x minus 2. X-intercept is going to be at 0, 0, 1, 0. And that y-intercept is at 0, 0. You can make a table for your graph, and you'll see that what's going to happen is it's going to look like this. You see how it kind of just brushes along kind of the same way those asymptotes do? And that's what it's going to look like. Now I'm just going to go through my domain. The range is messier because we don't know exactly where those points are. We'd have to do a lot of extra work to find it for this one. So my domain is all I'm going to care about. My domain, only thing I can't have is a negative 1. So negative infinity to negative 1. And the union of negative 1 to infinity. Don't worry about the range for that one. And let's do one more. Now my vertical asymptote, x minus 1 equals 0, so x equals 1. The horizontal asymptote, the numerator, is 2. The degree of the denominator is 1. 2 is greater than 1, so there is no horizontal asymptote. But since 2 is exactly 1 more than 1, there is a slant asymptote. So the slant asymptote, now I'll show you what it looks like if we did synthetic division. Set x minus 1 equal to 0, so x equals 1. And on the inside, 1, negative 1, negative 2. 1 goes on the outside, bring down the 1. 1 times 1 is 1. You get a 0 and a negative 2. Remember, the remainder, that's x, constant remainder. We don't care about the remainder. But our slant asymptote is at y equals, and it's just x. There's no other number there for the constant, so y equals x is our slant asymptote. You could also use long division. It doesn't matter. Y equals x, it goes through the origin. Looks like this. The vertical, x equals negative 1, looks like this. So now our x-intercept, real zeros of the numerator. So for our numerator, 0 equals x squared minus x minus 2. X minus 2 times x plus 1. So x equals 2 and x equals negative 1. So 2. Oh, I'm sorry. My vertical asymptote, I wrote in the wrong spot. It's x equals 1. I put it at negative 1 by accident. That's why it looked weird. There's negative 1. Now my y-intercept, y equals 0 squared minus 0 minus 2 over 0 minus 1. So y equals negative 2 over negative 1. Y equals 2. So my vertical asymptote, x equals 1. Horizontal asymptote doesn't exist. There is none. Slant asymptote, y equals x. X-intercept, it's at 2, 0, negative 1, 0. Y-intercept is at 0, 2. And when you draw the graph of this, it's going to, like I said, it's going to kind of work its way along those asymptotes. That's what the left-hand side looks like. And the right-hand side, going through that x-intercept, is going to look like this. And you'll see the graph there as well. We could find the values using the table just to save a little bit of time. So our domain, we just can't have x equals 1. So it's going from negative infinity to 1 and the union of 1 to infinity. And our range, we just can't have, well, we can have everything. It goes all the way up and all the way down. So it's negative infinity to infinity. And there you go. That's our new part, is the slant asymptote. It only occurs when the degree of the numerator is exactly 1 more than that of the denominator. Okay, that is it for chapter 2, and I will see you in the next video.